Hi, everybody. Happy Friday, happy Halloween, official Halloween. Remember, there's a guided tour of the ridges today at 5. All right, we're continuing section 4.4, which is curve sketching from Stewart. We started this on Wednesday, and you have the handout, the graphing strategy. And on Wednesday, we did an entire example involving a cubic polynomial. And then we started another example involving a rational function. In those examples, we just marched through the graphing strategy. And it took a long time. The first, as I mentioned in class on Wednesday, these problems take a long time, the graphing strategy problems. But there are different ways of approaching problems where you learn different kinds of things. And so today I want to do some stuff with the graphing strategy where we approach problems of a different sort, and we learn stuff about the graphing strategy by coming at it from a different direction. So before I start, though, so you have this handout that's 3 different rational functions, f, g, h. And I want to review a little bit about rational functions before we start. First of all, when a rational function, remember, is a ratio of polynomials. When are those things continuous? Or when are they discontinuous? Marceline?
They're continuous when the denominator does not equal 0?
Yeah, so they're continuous everywhere the denominator is not 0. So the only bad x values are the ones that cause the denominator to be 0. So everywhere except when the denominator equals 0. Now, how about this? When is this expression equal to 0? Give the x values. Yeah. Let me ask another question too. When is this equal to 0? All right, so everybody look at those 2 equations. Now, answer this question. Yeah, never. Because remember, x squared is always going to be greater than or equal to 0. So x squared plus 25 is always greater than or equal to 25. It's always a positive number. Now, when is this true? Gwen? Yeah. That's because we can factor this. X squared minus 25 equals x plus 5, x minus 5. Having roots means you can factor something. If you can't factor something, there aren't any roots. And if there aren't any roots, then you know you're not going to be able to factor it. So that's going to be key, because if you look at the rational functions in your handout, some of them have x squared plus 25, and some of them have x squared minus 25. That's going to be a big deal, because the ones that have x squared plus 25 in the denominator, those rational functions are going to always be continuous. All right, now, I also want to talk about the effects of factors on the graphs of functions. So a factor of this form, this is called a linear factor. Its graph is a line. So if you have a factor like that in the numerator of a function, in this case, I don't even have a denominator, what effect would that factor have on the graph? Let's go on to this, either one of these. What effect does the factor x minus c over x minus c have on the graph of this function?
Does it show a restricted value?
Be more specific. What do you mean? What do you mean by that?
It won't equal C.
Yeah, it's definitely x equals c is not in the domain, so there's no y value there. Same thing here. There's no y value at x equals c. Now, how does the behavior of this function differ from the behavior of this function? What's going to be going on near x equals c in this function? Gwen?
The top one will have a hole for x equals c.
Wonderful. There's a hole in the graph at x equals c. Now, why is that? Well, let's check. The limit as x approaches c of x plus 2 x minus c over x minus c, well, you know, it's last time in October that I get to do this. Since x is approaching c, we know that x is not equal to c, so x minus c is not equal to 0, so we can cancel. So that we still have the limit. We haven't done the limit yet. The limit as x approaches c of x plus 2. But now we can use direct sub. We just get c plus 2. Oh, that's a number. So that means that the graph is approaching the location c comma c plus 2. The graph is heading for the location x, y equals c plus 2. Now, it doesn't really matter what I have next to it. This could have been e to the minus 15x plus tangent of x cubed over 13. Doesn't matter. Whatever is sitting here, if you put a stack of factors like that next to it, it pokes a hole in the graph. And you can find the limit, and that tells you the xy coordinates of the hole. Now, what goes on in this graph? What does the x minus c in the denominator alone cause in the graph? Marceline?
Because it's a vertical asymptote.
Yeah, and where?
X. C.
Give the line equation.
Or just y equals c.
Nope. That's why I asked, because there's like a 50-50 chance you'll get it wrong. What's the format for a line equation for a vertical line? X equals c. So there's a vertical asymptote at x equals c, caused by this factor in the denominator alone. So that's actually stuff you probably had in classes before you got to this class. All right, so what I'd like to do now is turn our attention to this handout. Where's my handout? And I would like to think about, in this handout, a ton of work has been done for you. Finding these derivatives is a quotient rule problem, and those get pretty hard. And like this one's not so hard. You get here pretty quickly, but to get here, you got to do some cleanup to get it to look like that. So there's a lot of work in doing these derivatives. And there's a lot of work in making these graphs. Hell, the graph's been done for you. This is a graphing strategy problem, and somebody else scooped you and they made the graph. But let's see if we can make sense of these graphs. So first of all, let's think about the analysis of f, or analysis of the function in step 1. So for instance, for this first graph, that means we're just focusing on that. Notice, the denominator is never 0. That function is, there are no vertical asymptotes. Furthermore, the numerator is never 0, so the value of this is never 0. So this graph has no x-intercepts. So we figured this out on Wednesday. There is a y-intercept at 0, 4, and we know that it never touches the x-axis and it doesn't have any breaks or jumps in it, so apparently it's going to live its whole life above the x-axis. And on Wednesday we discussed the fact that when you plug in negative x, you get the same thing as what happens when you plug in positive x. So the left side of the graph is a mirror image of the right side. We discussed the fact that there are asymptotes. So there we go. There we get this graph that has all that nice smooth stuff. So now let's stick with the idea of doing step 1 analysis. Let's go down and think about step 1 analysis for the next function, g of x. Look, our denominator now has something that can be factored, x plus 5, x minus 5. Gwen would tell us that the denominator is 0 when x is 5 and x is negative 5. Those factors that are in the denominator alone are going to cause vertical asymptotes with line equations x equals negative 5, there it is, and x equals plus 5, there it is. What about other stuff? What's the y-intercept? Want some new hands here. You're college students, Math 2301. You're being asked to find the y-intercept. Go. How do you find the y-intercept? You could say asking for a friend. Oh, say it again? Yes, because you plug in x equals 0 and you get y equals negative 4. So sure enough, there it is. How about the x-intercepts? You're shaking your head. There is none. Why? The numerator will never be 0. Notice there are no x-intercepts on this graph. What about horizontal asymptotes? Well, what happens when x gets really, really big? The denominator gets really, really big. So the fraction gets really close to 0. So the y values get really close to 0. So in other words, the limit as x goes to infinity of g of x is 0. So there's a horizontal asymptote at 0. What about symmetry? What happens when you replace x with minus x? Well, g of minus x would be minus x squared, but that's just the same as x squared. So the y values of g of minus x are the same as the y values of g of x. In other words, the left side is a mirror image of the right side. All sorts of cool stuff. So notice the graph only changes sign at, I should have introduced, I didn't realize our book doesn't introduce the term partition number. From now on in this class, I'm going to introduce that term because it's a really important term. The partition number for a function is a number that causes that function to be 0 or discontinuous. So this function is never 0, but it is discontinuous at x equals minus 5 and at x equals 5. And notice, at those places, the function changes sign. So partition number is a useful thing. All right, let's go down and look at h of x. Look, now we're back to having a function that has an x squared plus 25 in the denominator. So no discontinuities. So no vertical asymptotes. What's the y-intercept? How about I don't have to beg to get the y-intercept out of you all? Yeah. 0. Y equals 0. Because when you plug in x equals 0, you get y equals 0. What are the x-intercepts? Also x equals 0. Because that's the only thing that will make the numerator 0. So that's going to be the only one. Sure enough, that's the only x-intercept. And notice again, there are no discontinuities. So there is one partition number, x equals 0, because it causes the function to be 0. But there are no partition numbers of the other flavor. And sure enough, at that partition number, it turns out that the y values change from negative to positive. Now, this is cool. Symmetry. We want to investigate what happens when I replace the symbol x with the symbol minus x. Sorry, all of you. So h of minus x is going to be 100 times minus x over minus x squared plus 25. But that minus can come out front. And in the denominator, minus x squared is just the same as x squared. Oh, but I can go ahead and bring this minus sign way out front. Minus in front of the whole thing, 100x over x squared plus 25. But this baby is just h of x. So I have a minus sign in front of h of x. So h of minus x is minus h of x. That's what's called odd symmetry. So it's an odd function. What does that mean? Means that the one side is the upside down mirror image of the other side. Look, there it is. One side is the upside down mirror image of the other. Asymptote behavior, you can see there's still going to be a horizontal asymptote at y equals 0. All right, now let's move on to step 2 analysis. So step 2, we look at f prime. So let's go up and look at the f prime. So that's the red graph. Notice f prime is a rational function also. It's never discontinuous because its denominator is never 0. So there is always a derivative. When is f prime equal to 0? Marceline? The denominator is never 0 at x equals 0 because it causes the numerator to be 0. So at x equals 0, there should be a horizontal tangent line. Aha, there it is, horizontal tangent line. Furthermore, the thing in the denominator, remember a while ago, before I put the screen down, it pointed out that this denominator is always a positive thing. But look, the numerator is capable of changing sign. When x goes from being negative to positive, this thing changes sign. So if f prime changes sign, that means that f changes from increasing to decreasing or decreasing to increasing. Sure enough, at x equals 0, f changes from increasing to decreasing. Let's look at g of x. Do step 2 analysis on g of x. So we're looking at g prime now. So notice that g prime is discontinuous at 2 places because the denominator factors. When x equals -5 and when x equals 5, g prime does not exist. That's fine because there's not even a point in the graph at that point. When is g prime equal to 0? Brendan, you raised your hand, sort of. When is this equal to 0? Look at the numerator. When is that? When x is 0. Sure enough, when x is 0, there is a horizontal tangent line. That's the only horizontal tangent line on the whole graph. That's the only place, well, actually, it's not the only place where f prime can change sign. F prime can change sign whenever, so the partition numbers for f prime are the numbers that cause f prime to be 0 or undefined. So there are 3 of them, at -5, or that cause f prime to be 0 or discontinuous. So -5 is 1, 0 is 1, plus 5 is 1. So those are 3 places where f prime could possibly change sign. But it turns out that, remember, well, the thing in the denominator, if it exists, the thing in the denominator is either going to be 0 or it's going to be a positive number, because I've got a number inside that might be 0, might be positive or negative, but it's squared. So that means that this result is going to be either 0 or a positive number. So the denominator never changes to a negative thing. So g prime can only change from positive to negative when the numerator changes from positive to negative or negative to positive. And sure enough, look at this graph. Increasing, 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 increasing again. Even though I had this wacky thing, when it recovers from that asymptote, it resumes being an increasing function. Only here does it begin becoming a decreasing function. And then there's the wackiness of the asymptote, but after that, the graph resumes decreasing. So really cool to look at these graphs in light of what we've learned about function analysis. Now look at this. This f prime, h prime, is never discontinuous because the denominator is never 0. But look, what are the values that cause h prime to be 0? Gwen?
0.
No, you said it before. Look at the numerator.
5.
And
-5.
yeah, exactly. That's why I called on you. That's your answer. For today, whenever I call on you, it's 5 and -5. So there are going to be 2 places where h prime equals 0. So the graph should have 2 places where it has a horizontal tangent line. Sure enough, those places. If I make the factors for this, if I make a sign chart for this, that's always positive, the denominator is always positive, there's always a minus sign in front, but these things can cause signs to change. So notice, they do. Decreasing, and then increasing, and then decreasing, because I have an x plus 5 and an x minus 5. Those are my partition numbers on my sign chart. Now, just a few more minutes. Let's look at f double prime. F double prime tells us about what? Marceline? Concavity. Concavity is related to the second derivative. So if you look at, I talked about this briefly on Wednesday, kind of yelling at you as you're racing for the door. Notice that it looks like there are two inflection points here. Well, there should be 2 numbers that cause f double prime to be 0. We found out that there are. The 5 over square root of 3 and -5 over square root of 3, those numbers both cause, because this factors as this factors. So let's just write that down. F double prime of x is, I'm gonna pull out that 3. So 200 times 3. So when I pull out the 3, I just have an x squared, but then I have to divide the 25 by 3. And then that, I'm not going to call on you Gwen because it's not 5 and -5, but this factors as x plus 5 over square root of 3 and x minus 5 over square root of 3. Remember I said a while ago, getting these derivatives is hard, and then getting them in a useful form is also hard, even harder. Turns out this is a useful form, knowing that you ought to think about factoring this completely because you're going to want to know when it's 0. Now I can look at this and realize, oh, f double prime is going to be 0 at 2 x values. 5 over radical 3, which is about 3, and -5 over radical 3. Sure enough, in there somewhere and over there somewhere, there's an inflection point. And at those places, the denominator is always going to be positive. So at those places, the sign of f double prime is going to change. So the concavity is going to change type. Sure enough, changes from concave up to concave down to concave up. Let me just do one more, and then we'll call it a day with this. Let's look at step 3 analysis for the green function, g. Notice the numerator, so g double prime, so we're thinking about concavity, thinking about a g double prime. Notice this function, the numerator is always positive. The denominator factors as x plus 5, x minus 5. So it's undefined at...
Oh, it's cubed. Is it still undefined?
Same thing, though. The factors are still going to be there. Yeah, so at x equals 5 and x equals negative 5. So at those places, notice the graph changes from the g double prime changes sign at those x values. And notice g changes concavity. Concave up, concave down, concave up. So again, these graphing strategy problems are huge if you go at them from beginning to end. But there are all sorts of ways sort of diving in midway. And this kind of thing is really the spirit in which you'll use the graphing strategy in the future. You'll have a function. You can even have the computer find the damn derivatives. And you can make the computer make the graph. But then you've got to think about, well, so I've got all this stuff about the function and its derivatives. Why does the graph look this way? That's actually really cool. And then what I said on Wednesday, it makes you start to have eyes for functions. You look at a function and you realize, oh, I can tell what that's going to cause in the graph. All right, let's do the quiz.